So it's a pleasure to introduce our next speaker, Umberto Hryniewicz from Aachen. He will talk about quantitative refinements of various conjectures in 3D, Reeb dynamics, and some results.
Well, thank you very much, Leonardo. Really a pleasure to be back to Rio after a long time without the conference, the usual summer conference. Really a pleasure to be here. Okay, so I would like to start by stating two very well-known conjectures. The first is Weissen's conjecture, asserting that the Hebb flow of every contact form on a closed manifold has a periodic orbit. The second conjecture is the two-infinity dichotomy. The Hebb flow of every contact form on a closed, connected three-manifold has either exactly two or infinitely many periodic orbits. Okay. And I would like to make some criticism. It's not really so much as about these conjectures, but it's not so much as that they're not great conjectures. It's just that if you keep stuck to statements like this, it's very hard to move forward. So, let me just say what I mean. So these are strong statements about the collection of all Hebb flows but one might argue that one doesn't learn too much about the structure of a given Hebb flow from knowing that it has infinitely many periodic orbits, or even just one orbit. So I guess what I mean by this is that these are very strong statements, but the emphasis is really on the every. That's why they're strong, because the emphasis is on the every. It's a statement about every Hebb flow. If you look at one Hebb flow, okay, I want to study this Hebb flow here because I like it, and then you happen to know that it has infinitely many periodic orbits, I'm not so sure you're so much happy about understanding the structure of that Hebb flow from knowing that it has infinitely periodic orbits. Of course, this is polemic, just a point of view, so that we can talk about it. Okay, so if you want to keep the emphasis on all Hebb flows, very strong statements. If you want to shift your perspective to study, so looking for results to study a given Hebb flow, well, okay. So the all right. So this is in very sharp contrast to the case in 3D where there are exactly two orbits. And that's a theorem which was obtained in collaboration with Cristoforo Gardner, Michael Hutchins, and Hui Liu. So suppose you have, say, M closed, connected, three-manifold, lambda, contact form on M, such that Hebb flow has exactly two periodic orbits. Then so several things are true. First of all, M is a lens space. Or maybe first of all I should say the periodic orbits are irrationally elliptic. M is a lens space. Okay, it's actually, well, let's say if P is the order of the lens space, then you can even say that as a contact manifold, this is contactomorphic to the standard lens space. So for some Q. Okay, so here P and Q, so P is a positive integer, Q is an integer strictly between 1 and P. They're relatively prime, and well, I can define better the lens space. Someone wants me to. I'm including the trisphere just for the sake of making the statement shorter as a lens space. Then if you denote by gamma 1, gamma 2 the periodic orbits, T1, T2 the periods, the contact volume, the integral is the elasticity of the flow. Then, and if you have phi 1, phi 2 deciphered transverse rotation numbers. So this means that one takes let's say in S3, it just means that you take Cypher surface, you take a frame which is aligned with the normal of the Cypher surface, and you compute the rotation numbers, the transverse rotation numbers of the dynamics in this frame. then so several identities are true. So the volume is P. So P being the order of the Line space is P times the product of the periods. And it's also T1 squared divided by the rotation number, T2 squared divided by the rotation number. By the way, this statement here is just saying that phi 1, phi 2 are not rational numbers. So we have all the algebraic identities which relate to several symplectic topological dynamical invariants of the which are relevant in this context. They are satisfying the exact same assumptions that would be satisfied if that length. So if you'd be talking about a irrational ellipsoid and taking the quotient. Also, the self-linking number is determined. The linking number is determined. So here, self-linking number, linking number are now rational numbers because we're talking about line space, not three-sphere. So basically the same structure. So the two orbits form a link, and this link is like the quotient of the two orbits in an ellipsoid. In the case P is equal to 1, there is even actually a result saying that you characterize the transverse knot type of the orbit by saying self-linking number is -1, linking number is 1, and so on. So in particular, lambda is dynamically convex. And then finally, both gamma 1, gamma 2 span disk-like Birkhoff, so global sources of section. This just means that there is a way to encode the dynamics of the flow. So dynamics is encoded by pseudo rotations of the disks of the disk. Okay, so here when I say this is in sharp contrast to this case is because here we are actually describing all the symplectic geometry and all the topology of the dynamics, and everything is basically described. There is not much else to say, except that we have the freedom of seeing here some pretty weird pseudo-rotations, as Victor explained in his talk. But up to that, everything else is fixed. So this is the kind, I mean, these disks, they are part of a foliation in the complement. So they are parts of the leaves of foliations which are transverse to the flow in the complement of the periodic orbits. And because you have this foliation, then you actually have something which could be understood as learning something about the flow. Okay, so that's the first part of the talk. And now I would like to state refinements of conjectures like this, which are, say, a bit more quantitative, so that we can start playing with these conjectures in a way that we can start learning more about Hebb flows. Okay. So having filed my complaint, now I'm going to propose something to work with. Okay, so let me say first refinement of Weiss's conjecture. I'm going to say the conjecture only in dimension 3, but it might be very well that it holds also in any dimensions, but I'm not so comfortable in stating more than dimension 3. So the conjecture would be that isolated invariant compact sets of Hebb flows in 3D carry a periodic orbit. So isolated means, in the same sense that Victor explained in his talk, isolated as an invariant set. Okay, so no neighborhood of this invariant set contains an entire trajectory except the trajectories which are already in the compact set. And so this, the Weismann conjecture, then is the case where the invariant set is the whole manifold. Okay.
Why do you put 3D?
Huh?
Why do you put 3D?
That's because that's the case where I think it's actually very likely to be true. In higher dimensions, I don't know. But it could be that the conjecture, I mean, the conjecture certainly makes sense in higher dimensions. I want to stick to 3D just because. Okay. Now, I'd like to state a result. So one very hard case, the case where the invariant set is the whole manifold. One very easy case is the case where the invariant set is a periodic orbit. So a periodic orbit contains a periodic orbit. That's very good. So let me state one result in this direction. That's joint work with Patrice Lecalves. So conjecture is true for invariant tori. So if you see a Hebb flow in dimension 3, and this Hebb flow happens to have an invariant torus, and if this invariant torus is isolated, then it has to have a periodic orbit. And I mean, and then, okay, work in progress. We believe we can get much more general invariant sets, almost the full conjecture, but of course, the tools, we still don't have the proof. The tools, I mean, here one comes with all sorts of heavy machinery. There is ECH, which allows us to study some genetic situations. And then there is also the Lecalves-Yacoz results. And there is some other tools. So it's really not, proof is more like putting together big, yes? It should be true. I mean, it should be true. Yeah. I think it's open. Have an invariant set of area-preserving diffuse on a surface. There should be a periodic orbit there. I mean, maybe to be on the safe side, let's say Hamiltonian. Yeah. No.
For diffuse motions, you could try, there's a left and 6 point here.
Yes. Yeah, I mean, there is all sorts of things one can try, but as far as I know, not proved yet. Yeah, that's, I mean, this question I would ask to you, for instance. I mean, I don't know, really. I mean, I don't have a feeling. In higher dimensions, dimension 3 things are sort of special. You have much better tools. It fits very well with KM theory, right? KM theory, you have an invariant torus, And then you make some assumptions, and you get some tori nearby. Among these assumptions, you include the assumption that there are no periodic orbits, an irrational flow on these torus. So here, we make less assumptions. We just say it's isolated. We don't say all the other assumptions that come Km theory. But also, we don't get accumulating tori. But we do get that if there's no periodic orbit, it cannot be isolated. So, I mean, if you take as a fraction of the conclusions you get over the assumptions you make, it's, I would say, it's comparable fraction to the fraction you get from Km theory. Okay, so refinement of to infinity number 1. So the conjecture would be, okay, so again, you have a Hebb flow in dimension 3, right? So Hebb flow in a closed, connected, closed 3-manifold. So let's say n of t is the number periodic orbits with period less or equal to t. Then either exactly 2 orbits, or in the case of infinitely many, because we expect this dichotomy to be true, or the lim sup as t goes to infinity of the log of n of t divided by the log of t is at least equal to 2. So it's dichotomy will be the growth of periodic orbits is either 2 periodic orbits or the growth is at least quadratic. There is nothing, growths like the prime numbers, this shouldn't be sharp. So this means at least quadratic growth. That would be a quantitative refinement, trying to make this conjecture a bit more colorful, so to speak. And then in here, there is a result by Bernard Alba, who's here in the audience. Here, yeah, so you can ask him about the details. Asserting that if you have a Riemannian two-sphere, then, so this cannot happen, right? It cannot have only 2 orbits. So this has to be always the case. And so that's the case. So it's, geodesic flow, so for the geodesic flow. This should be compared to a theorem of Nancy Hingston, asserting that, so again, in this Riemannian two-sphere, you always have the lim infim of n of t times log of t divided by t positive. So, of course, in this context, proving a result for the lim infimum is much better than proving a result for the lim sup. It's a stronger statement. But the growth here is way bigger. This is growing like at least quadratic. And this is growing much slower, like t divided by log t.
This is dichotomy known from fins and metrics.
No, nothing's known, I think. So why does one expect this to be true? Because if you look at the surface diffeomorphism, if you have any kind of twist condition, which allows you to apply any kind of Poincaré-Birkhoff type theorem, eventually boils down to counting. So you have some interval in the real line, and it starts boiling down. It boils down to counting the number of fractions with written in lowest terms, where the denominator is less than something. How does this grow? So basically, proving things like this boils down to exploring the twist.
So 2 is sharp as a
2 is sharp, yes. A convex domain in R3, you mean? It fits very well with the, yeah, I think so, yes. No counterexamples, yeah.
So how do you see the 2 sharp to sphere? To sphere?
Yeah, if you have a sphere of evolution, then you have a little bit of twist. It basically grows like, it has an integrable flow, you can do the explicit computations. You can get down to 2, yes. Yeah.
So let me rephrase my previous question. So the proof of this theorem, using the proof of this theorem, cannot show that if you have a Finsler metric with infinitely many post-geodesics, then you have this group, right?
No. No, because the proof here boils down to, so there are 2 cases. Either you have some simple embedded closed geodesic, for which the return map to the corresponding Birkhoff annulus is defined. And then there you're talking about just, as Victor asked before, surface diffeo on these annulus. Then you have to work out with surface diffeomorphism techniques. Basically, this is done by Patrice Lecauves with his foliations and so on and so forth. Now, the case that one has to, the new case here is to handle the case where you have no surface map to work with. Okay.
Let's take something autonomous for a sphere and lead to the so you would expect a linear growth.
Quadratic.
It is quadratic.
Yeah. It's like if you have a little bit of twist, it's quadratic. So here, n of t is really the number of periodic orbits. I mean, nothing. It's really as it's written. If at some below some period there are infinitely many periodic orbits, then it's infinite. Yeah, if you have, like, say, below period 5, there is infinitely many periodic orbits, the growth is infinite. That's what I mean here.
One last quick question. So for what you said on Albrecht theorem, does it imply that an SDM implies quadratic growth?
No, the proof is not with SDMs. The proof is.
So this quadratic just doesn't look correct. But what about the Barber? What would you expect for the Barber?
I don't know. I mean, eventually boils down to some twist. Some twist means if you have, say, a little bit of, let's say you can apply Franck's lemma in the sense that you have a little bit of twist, then immediately it boils down to counting how many fractions are there with the denominator less than something on an interval, and that's all this quadratic growth. Okay, so let's say refinement of 2 infinity number 2 Okay, so again, say you have gamma 1, again I talked about Hebb flow on a closed 3-manifold. Gamma 1 and gamma 2, two different periodic orbits, not the same periodic orbit. Then you can talk about a certain number. I call it the systolic pairing. It's equal to the, now the manifold is S3, okay? Just to, manifold is S3 here, just to make sure. We can talk about linking numbers, but could also be stated in more general homology 3 spheres. So I call this number here. Here are the periods, right? There are the periods, the linking number, and the volume, the contact volume. Say systolic pairing. Okay. So now let's define by S lambda the set of numbers of this form. And let's define the systolic interval to be, the infimum of numbers of this form, the interval bounded by the infimum and the sup of numbers of this form. Okay, the systolic interval. And the conjecture would be that the following holds. So first of all, 1 is always there. Sorry.
Lambda is fixed,
Yeah.
and S of lambda is what? So it's those numbers for any pair of orbits.
Yes. Yes. So the conjecture would be that, first of all, 1 belongs to this interval. And now, so if the interval degenerates to a point 1, then you have two possible cases. Either exactly two periodic orbits, or every trajectory is periodic. And in every case, even if it's not the case that it's only a number, the set S lambda should be dense in this interval. So here, I mean, the dichotomy is a bit split. Here, 2 orbits means the interval degenerates to a point, and you have 2 orbits. Or you might have infinitely many orbits, and this interval be a point, but in this case, every orbit is periodic. And if this interval doesn't degenerate to a point, then you have infinitely many orbits, and these numbers are dense, spread out in this interval. A bit of a, say, probably one can be a bit more precise and say equidistributed on this interval or something like that, with some genericity assumption, but. Okay, so that's another refinement of this of the 2 infinitely many. Here, so let me mention. So let me define. So So let's enlarge this set of numbers by adding numbers of the form rho gamma gamma. This would be the rotation number of gamma on a cipher framing times the volume divided by the period square. Let's make a slightly bigger set of numbers, and let's define the corresponding enlarged systolic interval. So here there is a ongoing, so joint, say in progress, joint work with Cristofaro Gardner and Hutchins, where we would prove that yeah, it's always true that one does belong to this guy here, and if this guy is actually equal to the number 1, then you have these possibilities here, either exactly 2 or every orbit periodic. Okay, so some results. And now I'd like to, so are there any questions about the statements? It should be some kind of rigidity. This interval being just a point should be some rigidity statement about the flow. Yes, yes. Sorry, no, here, if it's equal to, okay, so okay, so so the question is, when are we? So when can we say we understand? I have flow on 3D. Okay, that's a very personal question, right? Everybody might have different answer. You ask, yes. No. I mean, the only thing it's saying is there, you know, that these numbers are all the same, equal to 1. But it could be, say, if you have a rational ellipsoid, then you have not every orbit has the same period. Okay. So now, having complained a bit about things, when can we say, okay, when can we say we are satisfied with an answer? And of course, that's a very personal question. Everybody, you ask this to 10 symplectic dynamicists, you get maybe 11 answers. So then, personal viewpoint. If we can, so the answer could be when one can find and understand a transverse foliation. To the flow. So transverse to the flow. Transverse. Because then you know where the flow is going around and you can start working with the flow. So there's a conjecture here due to ETNGs, certain that C1 genetically, a nowhere vanishing vector field on closed 3-manifold admits a Birkhoff section. And the Birkhoff section is, I'm not going to go into details, but it's basically a special kind of transverse foliation. There are a few periodic orbits, finitely many, and the complement of these periodic orbits fibers over the circle in such a way that the fibers are transverse to the flow, and you will have a finite return time, so you can talk about return maps. A special kind of transverse foliation. And still, I mean, I would emphasize, if one finds and understands the Birkhoff section, then one understands something about the flow. It doesn't mean that if you just say there is one, and you don't know where it is, you don't know too much about it, I'm not so sure you understand also too much about the flow. When you say results like, okay, there is always one, or genetically there is always one, this means you're, again, understanding a lot about a big class of flows. But about a given flow, not so sure. So there is a theorem, and that's obtained by Contreras and Mazzucchelli, and also independently by Collin, de Hornoir, myself, and Anna Rechtman, asserting that C-infinite genetic Hebb flows have, in 3D, of course, enclosed three-manifold have Birkhoff section. And now the result of Marco and Gonzalo gives one genericity assumption, which is, say, more well-known, say, more spread out in the literature. It's what we call, what Hoffer-Zusskind called strongly non-degenerate, periodic orbits non-degenerate, and you have transversality of intersections of stable manifolds of hyperbolic orbits. We use a different genericity condition. We use non-degeneracy of the contact form and that periodic orbits are equidistributed. In any case, both statements, both Marco can correct me if I say something wrong, but both statements are rely a lot on Michael's theory of ECH, and it's really not elementary proof. And it's very, and also, so again, I would argue that this is a statement about a bunch of Hebb flows, but not about a given flow. So not really a satisfactory answer from this point of view. But still can prove some applications. I mean, one application something genetically the Hebb flow has positive topological entropy. For instance, one application one can prove with this. Okay, so now I have my last 10 minutes. I'm going to try to finish with a different discussion. Okay, so I want to talk about a little bit of celestial mechanics and talk about another conjecture. I want to talk about right-handedness. And here I would like to emphasize here celestial mechanics because that's a realm where knowing things about genetic flows or knowing very vague things about every flow doesn't help too much to understand because it's a really small finite dimensional family of flows. So, okay, so I would like to consider the planar circular restricted three-body problem. Okay, so planar means the three bodies move on a plane. Restricted means one of the bodies has no mass, has negligible mass. And circular means that the other two bodies, which do have mass, they move according to a relatively circular solution of the two-body problem. So this explains these three adjectives here. So then one boils down. So one eventually ends up with a Hamiltonian system, which is autonomous Hamiltonian in 2 degrees of freedom. So the energy levels are three-dimensional. So we're talking about three-dimensional flows again. And so still, so Poincaré already studies the problem in a rotating frame. So here the two massive bodies are moving, say, M1, M2. They're moving on circular, relatively circular position around the center of mass. And this, because it's circular, the angular velocity is constant. And then you can take a rotating frame where instead of seeing the two bodies moving like this, you just have them standing still on an axis. And now the satellite is moving around. So the massless satellite is moving around. Okay. So that's here two-dimensional configuration space. All right. So it's surprising that after this non-inertial change of coordinates, the Hamiltonian is still autonomous. You can do the same trick for non-circular, but then you get something autonomous. You have these pulsating coordinates. Because then the angular velocity is not, everything's a bit different. And, okay, so then if you look at this miraculous Hamiltonian, which is autonomous, the range of the energy goes from minus infinity to plus infinity. There are 4 critical values, 5 critical points, and if you go energies, so if you look at energies below the lowest critical value, then you have the satellite is moving in one of these regions, either here, bounded so-called Hill regions, so either near a primary or near the other primary, or outside here. That's what I call I will refer to this regime as subcritical energies, below the first critical value. And so let's look at the dynamics on one of these bounded regions. Of course, the satellite can collide with the primary there, and then you have to regularize collisions. So let's say regularize collisions. And then after regularization of collisions, these energy levels, they become diffeomorphic to really RP3, or if you just want to, let's say, roughly S3. And the flow is a Hebb flow. Okay? So the conjecture is that, so dynamics on regularized energy level, subcritical. That's by result of Albers, Frauenfelde, Paternai, and Otto van Kort. That's a Hebb flow on S3. And the dynamics there is right-handed. That's the conjecture. And right-handed, I'm not going to define exactly what it means. It somehow means that the invariant measures are somehow linked. But there is a very strong consequence of right-handedness, which is every finite collection, finite non-empty collection of periodic orbits span a global surface of section. So now one does understand a lot about the dynamics. So for instance, one understands a lot about the knot types of periodic orbits which can arise. Every knot type has to be the knot type of a fibered knot. So very strong restriction on the knot type. Not only that, these orbits are linked because take an orbit, it spans a global surface of section. The other one has to go around and intersect it. And you have all this numerology about how the orbits behave. If you look at a global surface section, you look at some orbits, they are linking. It's not so hard to find some links for which you can apply Thurston-Nilsson theory to the return map of a given global surface section and get topological entropy. Of course, it doesn't happen always, but it's very easy to identify patterns. There's like a production of statements. Yes?
What's an example of something you understand there and not there?
Here? Yeah, for instance, here, say, one is given a periodic orbit. Then you know, okay, this guy spans a global surface section. For instance. Let's say one is given two periodic orbits. You say they're linked. One gives a third periodic orbit, linked with one with the other, and also with any cipher surface, which is the homotopy class of a given periodic orbit spanned by the other two, and so on and so forth.
I was thinking more about I thought you meant more about the dynamics.
Yeah, I mean, the periodic orbits, they have, say, knot types of periodic orbits, how the periodic orbits look like. They're positioned in a way that you know how they have to be relative to each other, positive linking number, and so on. So for instance, here, one is, if one can prove this conjecture for these flows, one can start looking at a result. So for instance, Libre, Martinez, and Simon proved that. So if you go a little bit up with the energy, eventually these Rio regions get glued together. Here there is a Lyapunov orbit. Lyapunov orbit and the homoclinics to this Lyapunov orbit are, the existence of this homoclinic is connected to King Oscar's Prize story and Poincaré's discovery of chaos. So basically you want to say, can you really prove there is a homoclinic to this periodic orbit? Again, I'm telling you a concrete system, concrete orbit. I want to find a homoclinic orbit to this periodic orbit. It's a hyperbolic orbit. So, yeah. One might take advantage of the global surface action, see if we can apply results in two-dimensional dynamics. Actually, I don't have much time to say what I really wanted to say about this Lyapunov orbit, but I just want to say that, so Libre, Martinez, Simard proved that for a small mass ratio, and energies, so slightly upper critical energy, slightly upper critical energy, meaning energy is slightly above this critical value here, there is a homoclinic to Lyapunov's orbit. There is a homoclinic there. They prove it for a small mass ratio. For arbitrary mass ratio, they have some numerical experiments. They can also say, okay, these numerical experiments, they allow the proof of the existence orbit of these homoclinics. But, so in this particular case, there is, we would really like to find certain kind of transversalization, which is a special case of a broken book known much before the broken books. So it's called finite energy foliation, which has this periodic orbit, hyperbolic periodic orbit in the binding, and other two so-called retrograde orbits in the binding. And if you have this foliation of these three binding orbits, one can find a homoclinic to this guy. And that's work in progress with Pedro, Kim, and Nayara de Paulo to try to extend this result using the foliations to find this homoclinic. And finally saying, okay, we can actually prove that one has a more conceptual proof of the chaos in this system. Okay. For instance, in this work here, we have some statements which apply to degenerate flows that we hope to apply here. All right. So, I mean, I guess what I want to say is that this question here, as I said, I mean, if you ask this to 10 people, get maybe 11 answers. But one particular way of answering this question is to find foliations which you understand. They're not just flying around, and you understand where they are. You can try to do something about them. Okay, so I think I'll stop here. Thank you.